At this very moment, an unobserved electron in the atoms of the air around you doesn't have a precise location. It exists as a ghostly fog of probability, a statistical smear of potential coordinates. According to the foundational mathematics of quantum mechanics, it is simultaneously everywhere it be and nowhere in particular. It is a pure, unadulterated potential. But the instant that electron interacts with a photon that then travels to your eye, the instant it is measured, that entire cloud of possibility vanishes. In less than a trillionth of a second, the particle is forced to commit, to choose a single point in space and time to exist. This isn't a philosophical thought experiment, it's a physical reality confirmed by a century of data. From early 20th century cloud chamber experiments to the ultra-precise quantum sensors of today. Our classical intuition, forged in a world of solid objects and predictable trajectories, rebels against this. We instinctively believe in an objective reality, a universe that unfolds according to fixed laws, entirely indifferent to our presence. The moon, we tell ourselves, is still there even when no one is looking. This deterministic comfort is the legacy of classical physics, a worldview perfected by Newton and given its ultimate expression in the concept of Laplace's demon, a hypothetical intellect that, knowing the precise location and momentum of every particle in the universe, could calculate the entire future and past with perfect accuracy. In that clockwork cosmos, observation is a passive act. It's like watching a film that has already been shot. You are merely a spectator, and your presence changes nothing. But the 20th century shattered that clockwork. Experiments began to reveal a universe that was not a film, but a script being written in real time. The Stern-Gerlach experiment of 1922, for instance, fired silver atoms through an inhomogeneous magnetic field. Classically, you'd expect a continuous smear on the detector screen, as the atom's magnetic moments could be oriented in any direction. Instead, the atoms landed in two distinct bands. They were forced to choose one of two possible quantum states, spin up or spin down. There was no in-between. The measurement itself constrained the outcome, pulling a definite answer from an indefinite state. This is the observer effect, and it is the most profound, most unsettling, and most reality-bending discovery in the history of science. It tells us that at the quantum level, the universe is a haze of possibilities, a cosmic whisper of what? And your simple act of looking, of measuring, of interacting is a profoundly violent act. Your gaze forces this ethereal reality to abandon an infinity of its potential futures, snapping it into a single definite state. To be clear, observation in this context doesn't necessarily require a conscious mind. As far as the physics is concerned, a Geiger counter, a photographic plate, or even a stray air molecule bumping into our electron is an observer. Any interaction that extracts information from a quantum system, any process that records a which-way path or a what-spin state, is enough to trigger this collapse from possibility to actuality. This shatters the classical division between the observer and the observed. In the quantum world, they are inextricably linked. The very act of gaining knowledge about a system fundamentally alters that system. This isn't a limitation of our instruments, it's a feature of reality itself, a principle enshrined in Heisenberg's uncertainty principle. You can know a particle's position with high precision, but you sacrifice knowledge of its momentum, and vice versa. The more you pin down one property, the more uncertain the other becomes. Reality, it seems, will only reveal one face at a time, and the question you ask determines the answer you get. This leads to a dizzying philosophical vertigo. If a particle's properties aren't defined until they are measured, what does that say about the past? In 1978, physicist John Archibald Wheeler proposed his famous delayed choice thought experiment, later confirmed by real-world experiments. In these setups, the choice to measure a particle's wave-like or particle-like nature is made the particle has already passed the critical point in the experiment that should have determined its behavior. The results are staggering. It's as if the particle knows in the past how it will be measured in the future. The very history of the particle seems to be unwritten until the moment of observation. It implies that the past, like the future, is not a fixed, immutable block, but a fluid landscape of probabilities that only solidifies into a concrete story upon measurement. We are not just spectators of a cosmic drama, we are participants, our every interaction sending ripples backward and forward through the probabilistic fabric of existence. This is the ultimate paradox, a universe that seems to wait for an interaction to define it. What then is reality truly like before anyone or anything looks? From that unsettling question emerges the mathematical heart of quantum mechanics and the most famous experiment ever devised, the double-slit experiment. First performed with light by Thomas Young in 1801, its true weirdness was only unleashed when physicists in the 20th century began performing it with individual particles, like electrons. The setup, as described in countless papers, including the foundational 1927 paper by Clinton Davison and Lester Germer, which first demonstrated electron diffraction, is deceptively simple. You have an electron gun that can fire single electrons one at a time. In front of it is a barrier with two thin parallel slits. And behind that is a detector screen that lights up wherever an electron hits. Now, if you close one slit and fire the electrons, they behave as you'd expect. They act like tiny bullets passing through the open slit and creating a single band on the screen behind it. No surprises there. But when you open both slits, classical intuition fails spectacularly. Even when firing the electrons one by one so they have no chance to interact with each other, they don't form two simple bands on the screen. Instead, over time, they build up a complex pattern of bright and dark stripes, an interference pattern. This is the signature of waves, where crests from one source add to crests from another to create a bright spot, and crests meet troughs to cancel each other out, creating darkness. But how can a single electron, a singly indivisible particle, create an interference pattern? It's as if each electron, traveling alone, somehow passes through as a ghostly wave, interfering with itself before landing on the screen a single localized particle. It is a perfect, baffling synthesis of wave and particle. This wave of possibility is what physicists call the wave function, and its evolution through space-time is described with near-perfect accuracy by the Schrödinger equation. This equation doesn't tell you where the electron is, it tells you the probability of finding it at any given point. The height or amplitude of the wave in a particular region corresponds to the likelihood of the particle being there. This probabilistic nature is formalized by the Born rule, a cornerstone of the theory. The probability of finding the particle at a certain point is the square of the wave function's amplitude at that point. Before the measurement, the electron exists as this wave function, a superposition of all possible paths, through the left slit, the right slit, and every other conceivable trajectory. But the moment the electron hits the detector screen, the moment its position is measured, something dramatic happens. The wave function, spread out across space, instantaneously and mysteriously collapses. The superposition of possibilities vanishes, and the particle snaps to a single definite location. This is the wave function collapse, and it is the central mystery, the measurement problem of quantum mechanics. What causes it? To find out, physicists tried to trick the universe. They placed a detector right at the slits, a tiny sensor that could tell us which slit each electron went through. The moment they did this, the moment they extracted that which path information, the interference pattern vanished completely. The electrons went back to behaving like simple bullets, creating two distinct bands on the screen. The very act of observing which path the electron took forced it to choose one, destroying its wave-like nature and its ability to interfere with itself. This is the observer effect in its rawest form. The universe refuses to show you both its wave and particle nature at the same time. The question you ask dictates the reality you see. This has led to over 90 years of furious debate, splitting the physics community into different philosophical camps. The oldest and most established is the Copenhagen interpretation, championed by Niels Bohr and Werner Heisenberg. It takes a pragmatic, almost agnostic stance. The wave function is just a mathematical tool for calculating probabilities. The collapse is a real physical event that happens upon measurement, and we shouldn't waste time asking what reality is before we measure it, because science can only speak about what is measurable. It divides the world into a fuzzy quantum realm and a definite classical realm where measurements happen without fully explaining the boundary between them. For many, this was deeply unsatisfying. In 1957, a graduate student named Hugh Everett III proposed a radical alternative. Everett argued that the wave function doesn't collapse. It always evolves smoothly according to the Schrödinger equation. When you make a measurement, say of an electron's spin, the universe splits. In one branch of the universe, you measure spin up, and a version of you experiences that reality. In another parallel branch, you measure spin down, and another version of you lives in that world. Every quantum measurement creates a cascade of branching universes, a vast, ever-expanding multiverse where every possibility is made real somewhere. In this view, the collapse is just an illusion, the experience of your consciousness finding itself on one specific branch of this cosmic tree. Other theories abound. The de Broglie-Bohm theory proposes hidden variables and pilot waves that guide particles along definite trajectories, making reality deterministic again, though profoundly non-local. More recently, cubism suggests the wave function isn't a property of the physical world at all, but a representation of an observer's subjective beliefs and knowledge about it. The collapse is simply the observer updating their knowledge. What all these interpretations grapple with is the undeniable link between information and reality. Whether it's a conscious observer, a mindless detector, or the branching of entire universes, the transition from quantum potential to classical reality is triggered by an interaction that creates a record. This profound truth means the universe isn't just observed, it's co-created with every interaction, leaving us with a staggering realization. Reality isn't just out there, it's also profoundly